Hi, everyone. I'm Thomas Vero. I am one of the people helping organize QRISE. And yeah, today's workshop is going to be given by Victory Amole, speaker from Infleqtion. And yeah, Victory is a senior quantum software engineer at Infleqtion, which is a leading quantum computing company in the field of quantum information. And today he's going to be giving a workshop on applications of quantum computing to modern physics, and more specifically, related to the challenge. The workshop will go over how quantum computers have been used to improve quantum technologies that do directly generate practical value, like atomic clocks for GPS. So yeah, please welcome Victory, and whenever you want to start, you can start.
Awesome. Thank you so much for the great introduction, Thomas. Yeah, let me share my screen so I can start this PowerPoint. All right, can y'all see this?
Yep.
Perfect. Then I can. Cool. So today I'll be talking about quantum computer aided design, which is I'll define the term later. And yeah, feel free to interject and ask questions. This is going to be a very informal talk. It will just be basically talking about Infleqtion's technology more generally and how this all ties into quantum computing. So I'm going to cover, I'm going to give a quick introduction to Infleqtion. And then after that, I'll be talking about, applications for quantum computers and potential applications for quantum computers. And then after that, I'll cover, applications of quantum technologies. Then I'll give a quick introduction to atomic clocks. And then I'll show how recent experiments that have used quantum computers and atomic clocks and merge them in together. And then, there are other quantum technologies that, potentially could be merged with quantum computers as well. And I'll leave some type of Q&A so we can discuss and kind of just work off this idea of not having quantum computers specifically be used for quantum computation. Infleqtion. So Infleqtion is a global quantum computing technology. We have offices in Australia, the UK, and then in the US. So in the US, we have offices in Chicago, Boulder, and Austin. Our headquarters are in Austin, Texas, and I'm part of the Chicago office. So the Chicago office is the quantum software org of Infleqtion. We build a diverse range of quantum computing technologies, atomic clocks, quantum RF, quantum receiver, and inertial sensors, BEC for Boise-Einstein condensate, and quantum computing, of course. So all these are basically tied to our cold atom technology, where we trap cold atoms and shine lasers on them. And by doing that, this very simple concept, you can create all these technologies. So this is a quick overview of our product delivery plan, which is, so I'll just give a quick overview here. Our quantum cores, what all our technology is built out of. We have atomic prisms, and we also have optical trapping technology. And we also have a quantum software effort, which is the group that I work on, which is a quantum computing software program that optimizes quantum circuits. Ticker's atomic clock, Skywire is our quantum RF, and Scorpius is our internal neutral atom quantum computing hardware. Give me 1 second, let me get a drink of water. Cool. Does anyone have any questions so far about what we do? Cool. All right, so yeah, practical application. So this is the fundamental problem of quantum computing, and it's the reason why commercial organizations work on quantum computing. So we're all hunting for practical quantum applications that will have a positive real-world impact. In fact, this screenshot here is a new XPRIZE quantum applications announcement that Google just released very recently, where they're giving $5 million for a team that proposes a practical applications for quantum computers. So this is obviously a very big problem if even like, Google's like, internally we can't find a practical application, so let's, have a public competition that people can just participate in to find these practical applications. With the history of quantum computing, so quantum computing started in early 1980s by the observation with Feynman, where he, as a physicist, he studied atomic systems, and he noticed that, classical computers can simulate atomic system range. So then he proposed the concept of using an inherently quantum system to simulate these quantum systems, and that will make it efficient. So basically, this is, in my mind, this is translated as basically asking, like, instead of asking like what are the practical applications of quantum computers, you can ask like what are the practical applications of quantum mechanics, because quantum computers simulate quantum mechanics, etc. So it's the same thing. The thing is, like, we live in a classical world, so most applications, most of the things you use quantum computers for are not really like things that, real world day-to-day things you interact with are amenable to that type of work. And so pre-Shor's algorithm, which is the factoring algorithm, and Grover's algorithm, the main application was simulating quantum systems. But this is obviously a small market because it's mostly just scientists. So I have a screenshot here of, like, a graph of modern physics. So you have, classical mechanics, quantum mechanics, relativistic mechanics, and quantum field theories. And if you look at, these applications for this section, you find like MRIs, lasers, atomic clocks. Try looking for other things like transistors, electron microscopes, but those happen to be just, I wouldn't really call those quantum. They're like semi-classical. And then if you ask yourself, what are the applications of, so what are the applications of quantum mechanics? You see like MRI is used for like medical diagnostics, lasers like barcode scanners, atomic clocks, GPS. And there are others that you can put here. So you have like these applications that you have this technology that uses quantum mechanics like MRI, and then you use that to do medical diagnostics. So it's like one step removed from the actual quantum mechanics that's happening. You also have, if you were to take like, the Bose-Einstein condensate that Infleqtion built, and you ask yourself, what is the practical application of this machine? You look really hard and then you see that it's like just basically because it's like a type of quantum matter, it really can only be used for like quantum research or like education. But then, you try to look online and you see like, oh, I mean, people have floated the idea of using BEC for like atomic lithography, but there are not a lot of like use cases for these types of quantum technologies. Now, if you ask yourself, the opposite of, what's the application of quantum mechanics, you ask yourself, what are the applications of classical mechanics? You find out that it's literally like everything, right? Like vehicles, telephones, penicillin. You could just list all the technologies that have ever been invented, bridges and stuff, and you see that they all apply classical mechanics. So then you ask, like, why is it like classical mechanics has just so many technologies that are coming out of it, while quantum mechanics, you're working really hard to find 4 or 5 big inventions. That's a really deep question, and something I'm going to address here, but it's definitely something to think about. So with regards to this challenge, jumping off of this, I'm basically trying to explore this idea of like, using quantum computers, not to directly do things like QML or do all these classical things that we care about, but to use it specifically to improve existing quantum technologies. So the atomic clocks is just going to be an example of how to use these types of quantum technologies. So hopefully you've seen the GitHub. Maybe I can unshare my screen so I can just show it here. Give me 1 second. Okay. So if I go to my repositories, can you all see this GitHub here?
Yep, I think so.
Okay, cool. So this is a challenge. We're giving you all the background of why quantum computer design is important. So basically, there have been experiments that use atomic clocks. I'll talk about these in the later slides. Yeah, so it's just to basically implement these circuits that these type of clocks that that are built out of quantum computers are, and study their behavior and see how you can improve upon them. Maybe build off their work that like Misha Lukin's group have suggested, et cetera, et cetera. So then let me continue with this. So what are atomic clocks? So a clock is basically something that counts time by using oscillations. So, the most basic clock would be the day, like the sun. It oscillates by going around and the same pattern every day. So you use this to just count how many times the sun goes around, and that's how you can tell the time. You can also use an atom to tell the time, where an atom gives off these frequencies that you can use to count how many times it oscillates off the energy. So that's giving something like this instability function, which you have this corrector that is detected. So basically, this laser gives off atoms, and then there's a detector here, and then this detector counts how many ticks the laser is giving off, and if that's off, then this clock correction will shift it so it's back on again. So and then yeah, that's basically the gist of what atomic clock is. You can do the exact same concept, but use a quantum computer. So so you can have these atoms be quantum states that you generate with a quantum circuit, and then your detection would just be your measurement, and then you can do your correction. So this looks really familiar to like a VQE type of experiment, and that's exactly what this Nature paper here did. They used 26 qubit ion trap machine to build a quantum computer, to build an atomic clock. So basically what they're doing here is they're using these gates to build an entangled quantum state, and then they use a classical optimizer to find the best parameters for optimizing this entangled state, and then based on that, they update their variational parameters and do this over and over again until their quantum computers are very precise clock, basically. And these clocks are like way more precise than clocks that don't use entanglement. So this is it's called an entanglement enhanced clock. The problem with this one is it's not VQEs like there are a lot of like instabilities that happen with just using VQE. So there's this concept of this hybrid quantum clock where you're not running VQE. What you're doing is you are doing mid-circuit measurement readout, and then you're reading out the entangled ancilla here, and that's a way that you can use to do this kind of detection and correction for a clock. And same exact concept as this one. You're generating these entangled GHZ states, and then these GHZ states are really good at sensing quantum sensing. And in this case, we were sensing time. So yeah, that's the brief overview. I will take some time clicking into these papers and walking through them. But basically, the conclusion is, what if quantum simulations is the only practical application of quantum computers? Basically, what if quantum computers are just like telescopes or microscopes? They're just a scientific instrument. What if they don't have any other use? Then you look at, the global market size for microscopes and telescopes, and you see that, like the global telescope market is like 1 billion. And then the global microscope market is 11.8 billion. It's really not like tech company worthy. Like it's not gonna make like trillions of dollars. But I gotta say, like, we shouldn't lose hope, even if quantum computers end up being a scientific instruments, because quantum computers are programmable, which means they're really versatile, right? So imagine you had a programmable microscope. So instead of just having, a telescope that's $1 billion, and then a microscope that's $18 billion market cap, you have, a programmable scope that can turn into a telescope or a microscope, and that's a combined value of $12.8 billion. So this is these are my references, and I'm gonna do some Q&A, and then at 12:30 we can actually dig more into these papers that I gave a brief overview of. This one here, the hybrid quantum clock, and the optimal metrology with quantum sensors. And with that, thank you so much. I'm not hearing anyone, so I don't know if.
I have a question actually.
Yeah.
Yeah. So we're still, from your presentation, I'm assuming we're still in the stages of determining whether there are genuine good applications for quantum computers. But with Shor's algorithm, is that not like kind of like a huge application, or are there problems with implementing Shor's algorithm, like even if we had like really good quantum computers?
That's a very good question that I didn't really touch upon. The reason Shor's algorithm is a great application, but I guess it's not really a problem. The kind of foil to Shor's algorithm is post-quantum cryptography, which basically means that, of course, like the things we encrypt now using RSA will be cracked by Shor's algorithm. But there is a huge classical industry-wide movement to move to post-quantum cryptography, which is immune to Shor's algorithm.
I see.
Cool. Any other questions?
Also, anyone feel free to type in chat throughout the presentation if questions come up.
Thomas, is it okay if we cut this at 12:30 or
Yeah, we can.
Okay.
It's all up to you. So whatever you think is best.
Okay. Yeah, because I just had left some time to actually go deep into these papers, just to give a more comprehensive view of how these types of clocks are implemented. But if people feel it's better for me to cut the meeting short, and then for people who are actually interested in participating in this challenge, I can always do like a call just for people who are interested in this.
Yeah,
So I guess
Oh, sorry.
I guess offhand, can someone raise people who are slightly better interested in this, raise their hand, and then I can, do a more deep dive. So, okay. Is it Sharon? Anyone else? Thomas, what were you saying?
Oh, I was just going to say the same thing as you did, just to raise your hand or type in chat if you'd be interested. Um,
It looks like
yeah,
more people are joining. Someone leave something in the chat. Okay. Okay. Oh, Joanne, if you can talk, can you tell us how much experience you have? Do you just get started like a week ago or a few months? Like how much do you know? You're still muted if you're talking, by the way. Okay, cool. Yeah, let me reach out to you and Leonid independently, and then we can do more of a deep dive on these quantum computer clocks. Does that sound good? Okay, can you post your email please? And then I can just contact you uh independently. Awesome, thanks. I'm writing it down right now.
I will say, this meeting is being recorded, and I'm sure people will go back and who weren't able to attend today and be interested in looking at this stuff. But also, again, it's up to you what you want to do. But I would say there would be interest in continuing today.
Oh, okay. Okay, cool. Okay, cool. I'll share again and then I'll just go through the paper.
Okay.
Let's see. PDF is opening up. Okay, cool. So the introduction, they basically say that you have quantum computers that have high entanglement gates with high fidelities. And then you can use this for, you can use there's an open question of using quantum information processing to improve quantum sensors. So then there are two strategies. So you can use entanglement to get the correlations between the probes that you're measuring the sensors of. Or you can have an ancillary system that basically a mid-circuit measurement system that does the metrology on the ancilla. This paper ends up doing the second one, but the optical this one here ended up doing the first method. I'll show this real quick as well. see. Yeah. So this one ended up doing the first method. So if you go back to this one. Okay. So yeah, so they do high entangled fidelity gates. And this here shows the type of CZ gates they have. This just shows the population state. So their entangling gates end up being like 99.93 fidelities. This is just a the device I built is two physical qubits here, and they measure the period oscillation. Yeah, same thing, GHG states, ancillary entanglement, and yeah, so this is where they use. So basically they have, okay, so they have qubits for their clocks here, and then they have qubits for their processor. So the processor is what actually generates the entanglement. And then, once you entangle, you leave it here to do the clock. You leave it as a clock and then do an ancillary measurement on it. And yeah, that's basically their whole gist. Yeah, I don't really, I don't, if you want to ask me questions, I don't really know what to say. Like, maybe I can just yeah, let's just cut this talk at 30 minutes, and then I'll leave my email for people who want to contact me, and I can do a follow-up talk with more detail based on questions y'all ask. Does that sound good?
Yeah, that sounds good.
Okay, perfect. Let me put my email here. Perfect. Yeah, feel free to reach out if this type of project interests you, and I'll be free to go into more depth. I left my email in the chat.
Oh, awesome. Yeah, thank you again for hosting. It was a really really nice presentation, and yeah, the challenge seems cool.
Sharon, could you post your email as well so I can reach out? Sorry, you have my email. So yeah, please just email me. Cool. Thanks, y'all. See ya.